Have you ever stopped to wonder why we only ever see one side of the moon? Look up at the night sky, and there it is, the same familiar face, night after night. But what about the far side, sometimes called the dark side, of the moon? Why does it remain forever hidden from our view? The answer lies in an incredible celestial phenomenon called tidal locking. This is a story about forces in harmony, billions of years in the making, shaping the moon as we know it, and playing an essential role in Earth's delicate cosmic balance. Let's break it down step by step. Billions of years ago, when the Earth and Moon were much younger, their relationship was very different. The Moon once rotated much faster than it does today. At the same time, it orbited closer to Earth, completing an orbit in a matter of days. This rapid rotation meant that, just like Earth, every part of the Moon's surface took turns facing the Sun and being seen from Earth. However, there's a rule in physics that governs the relationship between two celestial neighbors: gravitational forces. Earth's gravity pulls on the Moon, just as the Moon exerts a weaker gravitational pull on Earth. These interactions created slight distortions, or bulges, in both Earth and the Moon. But for the Moon, which is much smaller and less massive than Earth, the effect was far more dramatic. These distortions, known as tidal bulges, were the starting point for a transformation that would lock the Moon's rotation into harmony with its orbit. Tidal bulges are essentially stretches or deformations caused by gravitational forces. For the Moon, these bulges didn't stay in perfect alignment with Earth's gravity. Instead, they moved slightly out of sync due to the Moon's rotation. This misalignment caused a tugging effect, a gravitational brake that slowed down the Moon's spin over time. As the Moon's rotation slowed, it began to sync up with its orbit around Earth. Millions of years passed, and eventually, the Moon reached a state called tidal locking. In this state, the time it takes for the Moon to rotate once on its axis became equal to the time it takes to orbit Earth. This synchronization is why we always see the same side of the Moon, its near side, while the far side remains hidden from view. So, what exactly is the dark side of the Moon? First, let's clear up a common misconception. The dark side of the Moon is not always dark. It receives just as much sunlight as the near side. The only difference is that we can't see it from Earth. A more accurate name would be the far side of the Moon, the hemisphere that always faces away from us. The near side, the one we see, is characterized by vast dark plains called lunar maria, which are ancient lava flows, and bright highlands. The far side, on the other hand, is strikingly different. It's rugged, heavily cratered, and lacks the large maria seen on the near side. This stark difference remained a mystery until the advent of space exploration. For most of human history, the far side of the Moon was purely a matter of speculation. Since we could only see the near side from Earth, the far side wasn't observed until humans sent spacecraft to investigate. In 1959, the Soviet spacecraft Luna 3 made history by capturing the first ever images of the Moon's far side. What it revealed was stunning, a surface dramatically different from what we're used to seeing, marked by a dense network of craters. In 1968, astronauts aboard Apollo 8 became the first humans to see the far side with their own eyes during their orbit around the Moon. This once hidden part of the Moon, though invisible from Earth, opened a new chapter in our understanding of its geology and evolution. Beyond the fascinating phenomenon of tidal locking, the Moon's gravitational relationship with Earth is crucial for life as we know it. The Moon's gravity doesn't just affect its rotation, it also governs conditions on Earth itself. One of the Moon's key roles is stabilizing Earth's axial tilt, the angle at which our planet is tilted relative to its orbit around the Sun. Without the Moon, Earth's tilt could swing wildly over time, causing extreme climate shifts and unpredictable seasons. Thanks to the Moon's gravitational influence, our planet has relatively stable, predictable seasons that make life more hospitable. In addition, the same tidal forces that locked the Moon's rotation also govern ocean tides on Earth. These tidal movements play a significant role in Earth's ecosystems, affecting weather systems and coastal environments. The name dark side of the Moon is a catchy term, but it's not scientifically accurate. The far side gets as much sunlight as the near side. The difference is that the far side is hidden because of tidal locking. As the Moon orbits Earth, Different parts of its surface experience day and night, just like Earth does. Still, the phrase dark side lingers, adding a bit of mystery to this celestial neighbor. Tidal locking might seem unique to the Earth-Moon system, but it isn't. This phenomenon occurs throughout the universe. For example, many moons in our solar system are tidally locked to their planets. Even some exoplanets close to their stars exhibit tidal locking, meaning one side constantly faces their star while the other remains in perpetual darkness. Tidal locking offers scientists valuable insights into how celestial bodies interact. It also provides clues about a planet or moon's history, including its rotation, orbit, and gravitational environment over time. The far side of the moon, with its rugged landscape, has plenty of unique characteristics. Unlike the near side, it lacks extensive maria, likely because the crust is thicker on the far side, preventing volcanic activity from forming lava plains, as it did on the near side. It's also home to some of the moon's largest and oldest impact craters, offering a geological record of the solar system's tumultuous past. In 2019, the far side became the focus of international attention when China's Chang'e 4 mission successfully landed a rover there, the first mission of its kind. This highlights how much more we still have to learn about a surface that was invisible to us for most of human history. The story of the moon, particularly why we always see the same side, isn't just about celestial mechanics. It's a testament to the beautifully complex interactions that govern our universe. Tidal locking is a fine example of balance and harmony between neighboring celestial bodies, shaping not only the appearance of the moon, but also the conditions for life on Earth. When we look at the moon, we're not just seeing its near side or imagining its far side. We're witnessing a relationship that has been billions of years in the making, a gravitational partnership that plays a role in the stability of our planet. It's a reminder of how interconnected everything in our universe truly is. The next time you gaze up at the moon, consider the incredible forces that govern its position and rotation. The dark side may remain out of sight, but its story is just as fascinating as the side we see. It's proof of the intricate natural laws that shape our cosmos. So, take a moment to appreciate this celestial dance. The moon, in its elegant silence, tells us so much about the universe we inhabit.